Okay. Start the next talk. The next speaker is Jeremie Houssineau. The talk is Multilevel Monte Carlo and transport map.
All right. So yeah, once again, thanks to the organizer and thanks to you guys for being here in the fourth week of this workshop. I know it's the last straight line. So today I'll talk about multi-level Monte Carlo. So as I guess you've seen during this workshop, it's unsurprising since I work with AJ, and he's doing a lot of this multi-level stuff. But so the novelty here is we are basically mixing the multi-level idea with transport maps, and so it is quite a natural idea, and I'll try to convey that to you. And so okay, the outline is very basic. So I'll start with just describing again multi-level Monte Carlo. We've seen quite a few talks on multi-level, so I'll stay quite high level. If there are details that I'm missing, or if something is unclear, just let me know. Then I'll move to transport maps. I'll explain how the things can go together, and I'll try to give you some ideas how to justify the use of those transport maps. And I'll just show a few applications that we've been considering. So yeah, this is very high level. So it's the multi-level idea. Basically, you can apply it as soon as you can identify some basically levels of accuracy on your model. So I mean, the SDE case with different level of discretizations is the basic example, but there are other scenarios where you can have these sort of levels. And so, of course, the idea is to basically save time. Instead of doing all the computation at the highest level, is to do the computation on the whole range from level 0, the most coarse level, all the way to level L, the finest one. And so it's a trick to basically sort of be able to use, for instance, the computation at level 0 towards the estimation of at the finest level. So the really basic step is to write the target distribution as a telescopic sum. So level 0, the coarsest level is just on its own, and then we have basically just the difference between the target's distribution at different levels. So here I stay it's quite general because I'll apply it to different scenarios. So I don't want my notations to be too specific at this point. But of course, here we can see if we just do RID from all those distributions, we've done absolutely nothing. So the idea of multi-level is to get correlated samples from those successive distributions. And so for each level, for each term in this sum, we want correlated pairs, and we want them also to be independent from one level to the other. So from one term in the sum to another term on the sum. So I'll denote those coupled pairs XL and XL minus. So I don't write XL minus 1 because of course that wouldn't work with the previous term in the sum. But so this is once we have those pairs, this is a basic Monte Carlo approximation of that guy here. So here, once again, I could use this Riemann trick and trick, and for instance, make L random, so I don't have any bias. But I'll keep the model simple, and I just assume we have some maximum L, and this is not random. We could do it, but it doesn't really bring anything at this point, in terms of at least in terms of principles. So we look at the sort of basic Bayesian inference problem. We have some initial distribution, P0. We receive observation at integer times, all the way from 0 to capital T. And so to describe the state process that's behind and the generation of those observations, we have a Markov kernel Q. and a likelihood. So this is very, very basic, but so we can write the whole smoothing distribution in this form. So well, this is the basic stuff with proportionality, of course, here. And so yeah, in this notation, it's yk is the observation when the state is xk, and this is the transition of the sort of usual notations. So of course, the first example that comes to mind is the case of an SD. So if we take a sort of standard diffusion process with some possibly nonlinear drift, some non-constant diffusion. So we look at the Euler discretization of it. So, and here straight away we have, of course, we have a very natural notion of levels here. We take either very coarse discretization. So, for instance, if L equals 0, we actually jump directly between time steps. And then the next level, we add, between each observation, we add one more step, and et cetera, multiply by 2 the number of steps at every level. And so this is the sort of general expression of it. And so the kernel that we had before, the sort of generic kernel, here we can express it in a specific way as the sort of composition of 2 power L kernels KL like this. That since this is Brownian motion, so this is normal PDF. And well, I mean, those expressions are quite standard. And so here, well, so this, I have to change it a little bit here if we want to consider really the full smoothing distribution is not only the state at the integer times, but also at basically all the time steps between those observation times. And so this is quite high dimensional, of course. But that's our target distribution, and we, of course, it's very natural to apply the multi-level idea here. That's really the usual setting. So just to make it a bit more visual, so here we have the state that's in blue, and the observations are the red dots. And so this is actually this percentiles in red with different shades. I mean, and so we can see what the effect of the levels. So at level 0 here, of course, we jump directly between observation times. So we don't really estimate well the well, actually here is not. Let's not put it as an estimation problem, but just let's say there's the true posterior distribution on the whole smoothing distribution. So at level 0, of course, it's quite coarse and it's quite approximate. And we can see as we grow in levels, we sort of approximate better and better the sort of well, variance here that's behind. And so the state maybe doesn't change that much if you look at it, but I mean, we do have a much better estimation at higher levels. And this is indeed the smoothing distribution. So you can see it sort of the variance decrease even before the observation because everything's smooth. Otherwise, it would be a sort of abrupt change here. So I mean, that's the idea. But as a starting point, this is actually it's not even trivial to generate like sample trajectories on these sort of problems. Here, okay, we don't have so many time steps, but we know, for instance, if we just do a particle filter, it's going to be hard to have a lot of diversity, for instance, at the first time step. So this is, although I mean it's a basic example, but it's not even that straightforward in terms of smoothing. All right, so another case where we can use this sort of multi-level strategy is if we want to do large lag smoothing. And so let's say we're only interested in the smoothing distribution at the initial time step. So instead here, we could have some interval 0 to k, or that's fixed, but just for the sake of simplicity, we just consider the first time step. So of course, this is just marginal of the full smoothing distribution. There's nothing complicated here. And sort of natural idea is to think, well, I'm going to basically condition on more and more observations, and this is sort of going to give me a level. So the more observation I integrate, the more accurate basically this is closer and closer to this. So once again, using this sort of progressive smoothing distributions, we can apply the multi-level idea. Right. So the golden question is how to obtain those correlated samples, because that's really the key here. If we're not able to generate correlated samples between adjacent levels, then we have nothing. And it's not very surprising, since we just started with a telescopic sum. So there's not really a trick in the sum itself, but to get correlation in general is quite hard. But quite early on, so Giles, who also suggested those multi-level ideas, so mentioned that we can try to basically minimize the Wasserstein metric, and in 1D, this is just doing this, and I mean this we know, right? If we have the CDF here, let's say this is a fine discretization, this is coarse discretization, and this is the Wasserstein metric in 1D, and this corresponds to the idea of just sampling one random variable from a uniform distribution, and taking the inverse of the CDF of the fine and the coarse, for instance, discretization levels with the same random variable, and we obtain highly correlated samples here, ZC and ZF. So that's a natural idea, but in general, it might not be obvious to get the CDF, and in higher dimension, that also gets complicated. So that's where those transport maps, they come in the picture, right? So so we do something that is very similar, but so there are some differences. So now we have two target distributions. I could have called them coarse and fine, but in general, I just say pi and pi prime. And so now we want to find maps. So those are the transport maps, G and G prime, corresponding to pi and pi prime. And in particular, we want, we select some base distribution, eta. The really basic thing to do is just to take a standard normal of the right dimension, and the same dimension as the target distribution. And so the transport map in this case is the map G, such that the push forward of this probability measure eta is the target distribution. So in this case, the push forward takes a very simple form. It's just the inverse image. And so we want another transport map, this time corresponding to pi prime. So once we have this, we can basically do exactly the same trick. We can take some realization of our base distribution eta, map it through our two transport maps, right? And we obtain two correlated samples from our distributions. So this is a similar idea, and actually you can see easily the connection with the previous one. Since in the 1D case we can write this transport map with CDF, that's called increasing rearrangement, and that's actually one of the only cases where we know transport maps explicitly. In general, it's a hard problem, so here is the expression for the push forward for the density. So of course we have a sort of change of variable here. A term that appears. So again, you could say, well, that's okay, that sort of generalize the idea to higher dimensions, but it's still not straightforward to find those maps G and G prime. So one approach to do this is to introduce what's called a not Rosenblatt rearrangement. So it's a triangular map, and so in this case, lower triangular, but actually in general, we can also work with what people call sigma generalized rearrangements, where there's some permutation of the components. But for simplicity, I just consider here the basic one. And so if you look at the theory, you know that there's under some relatively weak assumptions on the target densities, this lower triangular transport map exists and is unique. So that's quite nice. And the other thing that's nice about it is when you write it in this form, actually all the terms are monotone increasing as a function of the last variable. And this is something that's easy to parameterize as opposed to just any arbitrary map. And so that's sort of a standard idea. And so for instance, we can assume that each component like this is the sum of a function with an integral of this form. So here you can have a square, or you can use the exponential of this function bi, where we only integrate respect to the last variable here. And so for instance, here we can assume that ai and bi are some probabilistic Hammett functions, or so in this case, depending on the order we consider, we can have, we have a really rich family of functions. And in the case where, let's say we take infinite order, we can represent any such map with this representation. And so then the idea is to find a map that minimizes the Kerr divergence between the base distribution and the target distribution through the map. So it's the nice thing also with these rearrangements is this term here can be written in a simple way. So we just have this sum over partial derivatives, and so this is a really doable problem. So of course you have sort of two-stage problem. You have here you have an integral, and then you have a minimization problem. But even if you do something relatively simple, you just take some kind of quadrature for your integral, and then you can minimize the problem. You don't, for instance, using some Newton method with conjugate gradient, and then you can solve this problem. And so this map is the sort of unique minimizer of this problem. So everything's sort of well behaved. And but still, it doesn't solve completely the problem, right? Because if n is very large, this is going to be very challenging. So the minimization problem is going to be hard. Just approximating the expectation is going to be difficult. So it sort of goes in the right direction, but it's not quite there yet. And so even if the dimension of the state space is low, so actually all the examples we've taken is the dimension is 1. But of course, this sort of extended smoothing distribution is on a very large space. So this would be extremely challenging to find a map in such a high dimension. And for the large lag smoothing application, although this guy actually only, for instance, in this case, is only on R, but we don't know it explicitly. So we still need to, for instance, find the smoothing distribution and marginalize it, or find some ways of finding this marginal. But this is not an easy problem in general. So this is something that has been solved by Youssef Marzouk and his team, and has been archived just last year. And so Youssef gave a talk the first week of the workshop, and he actually explained a sort of different way of tackling the problem. So it was in a case where you have an inverse problem and you've sort of large dimension in your state. But so here, the nice thing is we know exactly the structure of this problem. It's we have a HMM that's behind, and it has a lot of sort of conditional independence properties, and we know them. We don't need to learn the structure, or we don't need to sort of find an approximation. We just know it. We can use this to basically break down the problem into findings, several smaller dimension maps. Instead of taking this directly, actually, we basically only have to solve maps in R2. Now, for dimension D, for dimension 1, sorry. So in general, that would be R2D. But that's a lot smaller, right, than this. So And that would in general be doable. So, so here I'll just try to explain the principle and sort of hopefully convey why, how we can decompose this thing. It's not completely straightforward, but you see it's not too complicated either. So I'll just take capital T equal 2. So we only have 3 time steps, 0, 1, 0, 1, 2. And so as I was saying, the very standard choice for the base distribution is just standard normal. So in general, I write n1, n2, n3 for the standard normal in dimension 1, 2, 3. Right? And I'll just sort of write this shorthand for the likelihood. So I make the observation disappear, but I add the index to make it clear here, right? So so as I was saying, we can well, if you want to try to break down the problem in basically time step per time step, this is not going to work. Of course, you need to learn about correlation between time steps. So the minimum you can do in terms of breaking down the problem is taking 2 time step per 2 time step, right? So then so I just color in general the first time step basically. Well, the first 2 time steps is for x0, x1. So it's this whole term. So this is in general this is not too hard to find a transport map for this guy. And then we'll see how to basically bridge this with the second part of the term. So this includes x1 and x2, but here is just a conditional x1. So we'll see how that works. So for the first step, I mean, we just do it in a sort of straightforward manner. So as I was saying before, we actually have a slightly different map. Here is not lower triangular, but it's upper triangular, so it's pretty straightforward. And so what's interesting with the form of this map is, and in general, so here basically that gives away sort of marginal. So this map, 2-dimensional maps, goes from the standard normal of dimension 2 to our target distribution, the smoothing distribution up to time 1. But if we just take out the second component of the map, we actually have the filtering distribution at time 1. So that's a very useful property. We'll see why. So for the second step, there's a little modification here. So we don't want to have the filtering distribution or something here. Instead, and you'll see why it works, we just put again the standard normal on basically the equivalent of x1 on the state at time 1. But we reuse this map here. So in a sense, we are still pretty much connecting the filtering distribution at time 1 and the Markov canal on the likelihood at time 2. And to see this, actually, this normalizing constant, just by a change of variable, we can see that it's also equal to the normalizing constant if we have the filtering distribution instead of the eta here. So basically, it's up to a term. This is just a change of variable compared to the what you would write with just the filtering distribution here again, right? So so we can solve this problem once again, and this is only 2-dimensional. It's not too hard to solve the minimization problem, and we get a new map G1, and once again, so this doesn't really correspond like directly to something, but this we can show is also the filtering distribution at time 2. So we're building something that sort of has the right structure. There's this little tweak here, but we'll see that makes it work. So so as I was saying, this doesn't really correspond to something, but it's just a sort of change of variable compared to what we want. So if we want to do one-like smoothing, we just reuse this second component here, G02, and this we can show this is solve the one-like smoothing. So it's distribution of x1, x2, given observation up to time 2. And so here I put the variables in gray because it's just to sort of indicate them, but they're not actually there. I mean, those are maps. So so we're looking at this composition. And so this is good because if we can solve the whole problem just by doing composition, then we have a sort of recursive algorithm. Every time we just add one new map, and we don't have to recompute everything. So this is a sort of critical a critical property, and we'll see if we want the full smoothing, it also extends. So so now we have this one lag smoothing. I just sort of rewrite it here, and the second part of the map of the composition doesn't have anything to do with not directly with the state at time 0. So I just put identity here, and then I just replace here the first term I had in G1, and we can show that. Okay, maybe I'm not going to go through too much, but we can show that this actually we completely recover the transport map for our full smoothing distribution. So, and the trick is to basically look at the pullback, so it's sort of the opposite of the push forward, and using quite simple calculation and using the fact that the normalizing constant here is the sort of right normalizing constant. Basically, we recover that our map G, which is the composition, pullbacks our target distribution to our base distribution. So this is the right map, and so we could just continue to do this, find the map at G2 with the same sort of replacement here, and just continue. And this is called, I mean, it's not so obvious here, but in general, this is called embedding in the identity map. So we just put identity everywhere except on the two components where we're doing the calculations. And this would yield the proper transport map. Right, so let's go back to multi-level. So now we have a way of getting samples from for the full smoothing distribution. And so, or any distribution we want. And so in general, instead of having our XL and XL minus as before, we just use our transport maps, GL minus 1, and this is just the same random variable from standard normal. And so this is an approximation of our target distribution. So this is very doable. There are only a few tricks to solve the problem I mentioned. So for the SDE case, actually we don't have the same dimension between two different levels. We've basically added dimensions. So there's just some thinning. We just, instead of taking the whole standard normal vector, we take every other component or something like this, right? So nothing tricky here. It's just a remark. And so for the smoothing, we have this large lag smoothing, and of course we could just compute the whole or find the transport map for the whole smoothing distribution and generate samples and only keep the first dimension, but that would be a bit wasteful. And so another technique that's been suggested by Youssef Marzouk once again is to basically consider x0 as a parameter. And well, I didn't indicate again, but you can do exactly the same thing with basically adding a parameter, and this still works. So that's we can use exactly the same technique. So in terms of application, so again this SDE case. So we have the usual variance plus bias decomposition, and so the variance. I mean, here we just make pi L appear. So this is the Monte Carlo approximation. This is the true target, and well, I mean that's fairly standard as usual with multi-level. If we fix the error to be epsilon square, well, we can deduce something. So for instance, we can decide to which level we have to go, depending on epsilon and depending on the bias here. And if we want to optimize the cost for a given variance, given that the variance is in order beta, well, HL beta, and the cost is minus zeta, then we can deduce the number of samples we have to use at every level. So again, that's standard. And well, just as a sort of verification, in the 1D Gaussian case, we can verify that this is the order we want. Basically, it's so beta, the order of the variance is a square. So of course, that's the guarantee is only in the linear Gaussian case. So I mean, sort of usual visual model. But we also consider the Lange event to verify that empirically that this works also with a non-Gaussian distribution. So since our base distribution is Gaussian, you can see that the case where the target is also Gaussian is a very special case, actually. So you can expect that this technique will perform well. Actually, it's sort of related to, in this case, to the Laplace approximation. But so basically, if the target is also Gaussian, the transformer is extremely simple. It just is just linear plus constant. So in the linear Gaussian case, we really can expect that it's going to work well. So in a non-linear case, well, we have to verify this, right? So again, this is fairly usual. So first, we need to check that we get the right orders. So for the variance at level L, when we basically vary L, we have HL here. We can check that with something that looks like a square, and so the fitted sort of curve here is polynomial of order 2. And we also want to check that the cost is basically an inverse as a function of HL. So here, well, maybe the word order is a bit misleading. So this is for the order of the map. So if we go from order 3 to order 4 in terms of number of times we consider in the expansion, so of course we increase the computational cost, but this is still quite reasonable. For the Lange event case, we also basically get the same sort of results. So this sort of confirms that we get the right orders even in a nonlinear case. And so for the linear Gaussian case, so here I only consider filtering at the moment. So my test function basically just isolate the last variable. So here we just compare using multi-level with doing computation only at the highest level. We can see that, I mean, there's a significant gain, but again, we expect that it would work well in linear Gaussian case. So for the Lange event, we still have quite an improvement against the only computation at the highest level in the filtering case. If we want to do smoothing, so here I take a test function that's slightly different with basically it takes into account also some of the previous variables with some exponential decay. So here is a little bit more difficult. And so my understanding is that since we have this composition, so this is for the SDK, so we have a composition of a lot of maps, basically, and to 2 power L times T maps. And so every time we increase the level, we have more and more maps. And so when we do filtering, it's okay because we, even if we have maybe a bit more error, we only go through those maps once to get the filtering distribution. But if you start to do smoothing, you also have to evaluate the composition also to get samples. So you sort of go twice through the approximated map. And so I think the error that's generated when we do this is a bit higher. And so it's, in this case, it's a bit more difficult to work if we do smoothing. But again, the main property of the transport map that we use here is the ability to deliver couple pairs of samples. So we have, okay, some, this is a different case. Here we do this large lag smoothing. And so under the sort of usual assumptions, we can verify, so this is on the real line, but we can generalize this to RD using this rearrangements. So you can verify that basically the variance is bounded by this term. So in that's is power L minus 1. So this is what we want to see. And again, same sort of things. We can decide on the final time where we are going to stop integrating observations, depending on the error we want. If we want an error of order epsilon square, we can deduce the number of samples, and we'll know the cost. So the cost, there's an improvement here compared to with not doing multi-level. Which is, if T is large, it's quite substantial. So again, we consider 2 models, linear Gaussian, and this time we consider some stochastic volatility model. I'm not going to go through it. So we check that the order is as we want, both in the Gaussian and the stochastic volatility case. Right. So in the linear Gaussian case, we have some more detailed expression of the variance, but actually running a bit out of time, so I'm not going to discuss too much. But I think that's interesting. So this time we compared with the Paris algorithm, which is a particle-based technique to perform smoothing, and which is considered as a reference for this. And so in the linear Gaussian case, so Paris is, so here this is the number of particles, and so it's quite difficult to estimate the state at time 0, and we know with particle method it's generally difficult to do this. But if we use the multi-level ideas with a transport map, we depending on epsilon, log of epsilon here, we get really big gains. Once again, this is linear Gaussian, so we don't really expect to have a bias here, on a very small bias, because even a low-order map would basically be enough to characterize the transport map. For the stochastic volatility, we see that at some point we stop improving so much. So this is probably mostly due to bias, but we still basically get very low MSEs for very small cost compared to Paris. So I think that's also a very positive result. Right. So hopefully managed to convey that transport maps are very well suited to multi-level because of the ability to generate correlated samples. In general, I would recommend it if you have a sort of low-dimensional problem and you want to do smoothing. It works very well. It's very easy to obtain independent samples for the whole trajectory, which is quite unusual. And I think that's really one important feature of this. Yes, so we can get the full smoothing distribution. And what would be nice is to actually be able to quantify the error we make when you have a finite order approximation of the map. And this actually, we could use it directly in the multi-level ideas and have a sort of, for instance, sort of multi-index where we control not only the level, but also control the degree of approximation of the maps. So, but for this, we need to have some theoretical understanding on the error for a given level of approximation. So I would say generally, I mean, it's not very easy to implement. And there's so the transport map in themselves is okay, but also to do the Bayesian inference and to sort of manipulate those maps. But so fortunately, the code is available on the website of the team of Youssef Marza. And so it's in a Python package. So I had to learn Python to use the package, but it was worth it. So I think it would have been a bit complicated to re-implement everything, for instance, in MATLAB. But so the package is there, and it's quite multi-purpose. So if you want to try it out, I would recommend you do. All right. So yeah, the references, and that's it for me. Yes, but we, as I was saying, we're also online actually. So we just basically add. We have a discomposition of maps, and for every new time step, we can just add one new map. So it's literally online.
To get the smoother, you still have to compose backwards.
Well, so in this case, yes, yeah. So in this case, so I didn't want to go too much into the details, but what we used is the. It's at the beginning. So we consider x0 to be a parameter. Was it here? Oh, okay, it doesn't matter. We consider x0 to be a parameter, and then you can basically you can propagate online the map from to the distribution of x0 given all the observations. So basically, in theory, you would have this composition of maps, but you can reapproximate it by one single map every time step. And so this is online. That's why we compared with Paris. So there's no reevaluation of the whole composition to get samples.
If you get a sample from the smoother at time 0, you would still have to compose all these maps.
No, because we approximate the composition of maps by one single map.
Is that accurate?
Well, yes. The accuracy, I mean, in theories, it would be difficult to verify, but in practice, we get good results. So at the moment, it's only practical verifications.
Usually mean squared error. And did you calculate the LP error?
No, we only look at the mean square.
Technical difficulty or is it some other?
No, it's no, we didn't consider it.